Hello everyone, and welcome back to our class in Artificial Intelligence and Machine Learning in Finance. In this video, I want to show you the application of penalized linear regression models, that is rich regression, the Lasso, and ElasticNet. And we'll use it in the R program. More precisely, we'll be using the Risk Analytics R package. And if you still need to download this, you can access the cursor here. You can access the package here under this link, and we will also need a list of ticker symbols and some additional data for the stock market returns that you can download here. And what we will try to do is we will use numerous features, numerous explanatory variables or numerous regressors, and we'll try to forecast equity returns. More precisely, we'll try to forecast the returns on the Apple stock 1 day ahead. So this is a very simple task in finance, forecasting equity returns, and ideally we'll identify those features in our data that can help explain the response variable, which in this case is just the 1 day ahead Apple stock return. So this is our task. The application is actually quite simple, but as you can see from the next couple of slides, this will take some while to do in R and to implement all these functions. If you remember one of the first videos, you will recognize on this slide that actually we're not starting with the regression models itself, but we'll start with importing and pre-processing the data, because this is one of the more important steps that usually you will not find in numerous textbooks. So everyone always starts with the models, but actually you need to work with the data beforehand to bring it into a form so that it can be processed by the models from machine learning. First of all, we have to start with an even more trivial task. We need to install the R Risk Analytics package, and it cannot be installed directly from a CRAN mirror. So actually you have to download it, and thus you will probably need to use these two programming lines here, library DevTools, and then install the Risk Analytics package from GitHub. Then you need to load it into the memory in R. So library Risk Analytics. We also need the Snow and the QuantMod package. We need to set the file path for the downloaded CSV file that includes the NASDAQ ticker symbols. Why? Because actually we want to rename some of our variables which have not very practical names and designated names in R, but we want to make it more easier to interpret. So we download the NASDAQ ticker file, CSV file, and then set the path NASDAQ to the file path where the NASDAQ ticker.csv file is saved. And then we read the NASDAQ's ticker symbols into company list. We order the firms in descending order by actually market capitalization, which is included in this data array. And what we'll be doing next is we'll be choosing companies, and we'll only be working with those companies that have a very high market cap. So that's why we download the data, we read the CSV file into company list, and then sort the company names in descending order by market capitalization. So that's what happens in lines 12 and 13. Next, we need to download the return data for those 10 companies which have the highest market capitalization. So stock data will later include the stock returns, and we define it as a data frame, and then we need to get Yahoo data for those companies that are included in the object company list. And let me get my cursor here. We only use 10 companies. You can easily extend this application to more companies. You will later on see why this probably doesn't make too much sense, but nevertheless we'll be using 10 companies. And we're using data from 2010 to 2020, and we are using the stock returns. We'll also use macroeconomic variables. We get those via get macro data, and we are saving it into the object macro data. Next, we manually add the corresponding date to each row. This is a rather complicated command, and you can see it will be saved into the object dates. Those are the row names as matrix, get symbols, etc., etc., for several of our variables. And then, last but not least, we assign those dates as row names for the macro data. Okay. Now, the variables that are contained in macro data in this object have variable names that are not too practical. For example, head VIX, 1 GSPC, these are the S&P 500 returns, 3M TCM are the changes in the 3-month treasury bill rate, and we'll rename some of these variables. For example, we'll, instead of pound head VIX, we'll simply call it VIX. Instead of 1 GSPC, we'll call it SP500. So this is more intuitive than the previous names. And this is what we'll do in line 9. So the column names of the object macro data, they are overwritten with VIX, SP500, real estate, TR3M, yield, and credit. And by the way, these are the macroeconomic variables that we'll be using. So implied volatility index, this is the volatility index on the S&P 500, the S&P 500 itself, the iShares Dow Jones US Real Estate Return Index, and then the yield, the slope of the yield curve corresponding to the spread between the 10-year Treasury rate and the 3-month T-bill rate, and last but not least, the changes in the credit spread between BAA-rated bonds and the Treasury rate. So this is a credit spread. Okay, now we also need to pre-process the data in some other sense. We'll add a date column to both macro data and stock data, and then merge it via the merge command in line 5 to have a new data object that is complete data. This includes the macroeconomic and the stock market data all in one data frame. Next, we'll redefine complete data as a tibble. I told you in a previous video that this is more convenient in many machine learning applications, in R at least. And if we now print the first 5 rows of complete data, you can see that these are the first 5 observations. You see the dates, and then as columns you see AAPL. This is the ticker symbol for the Apple stock. MSFT, Microsoft, Amazon, Google, and it then goes on. And we have 2,761 more rows, so all in all about 2,800 objects, 2,800 observations, daily observations for our stocks and the macroeconomic data. And you can see we have additional variables, for example, JPM, JP Morgan, J&J is Johnson & Johnson. We'll actually see this in our results later on quite prominently. Johnson & Johnson, nowadays everyone knows about this company, and so on. And you see VIX, SP500, real estate, and so on. These are the macroeconomic data variables. We, again, extract the macroeconomic variables from complete data because the dates in the original macro data object do not coincide with the dates in stock data. So we'll extract it again from complete data to have corresponding dates in all our objects. And if we now print the correlation matrix, we get a first hint what the data looks like. We'll see which variables are correlated, and this gives us a first idea of what the data looks like. You can also do this for the stock data. You will see, of course, different correlations, and it would also make sense to print out summary statistics. Summary statistics that will include the mean, the variance, the standard deviation, or volatility of the data, the quantiles, minimum, maximum values, to see if anything is off, that anything might be an outlier that needs to be dealt with. We could have a look at the correlation between the macroeconomic and the stock market data. And here I've only shown you the correlation matrix for the macroeconomic variables. You can also visualize this via the library callplot, and then the command is also called callplot. And here you can see, for example, that there are some strong positive correlations between real estate and the S&P 500, or, well, this is the same, and also a slightly negative correlation between the VIX and the S&P 500 and the VIX and real estate. So this is just another way of showing the correlations and a visual way. Okay, now as you remember, in statistical learning and machine learning, we need a training data set and a test data set to see the out-of-sample performance of our models. And we do this, first of all, we load the library lubridate and then split our data into training and test data. This looks like it's quite complicated, but actually it's just using the complete data frame and selecting some filters. For example, the year is smaller or equal than 2008. Where's my cursor? Here it is. It's smaller or equal than 2018. So that's the training data. And 2019 and 2020, those are our test observations. So 18 years training data, 2 years test data. And because we later on want to forecast, we want to predict the 1 day ahead returns on the Apple stock, we set another column, that is test data $forecast, to be the test data of Apple, and same here for the training data, and we switch it 1 day ahead. So we're using the Apple returns, and by switching it 1 day ahead, you get the, for example, if this were the 1st of January, then for the observation of all our variables on the 1st of January, you would have the observation on the 2nd of January of the Apple stock as an additional column for the response variable that we want to forecast or want to predict. So that's actually test data $forecast and training data $forecast. We keep in mind that this is just the Apple stock return, just 1 day ahead. It could be also a quite different response variable that we want to explain with our data. And then, because some of the models need dependent and explanatory variables, the response variables and the predictors in separate matrices, we do exactly this. We take training data, we take test data, and we split it into X-train and Y-train and X-test and Y-test here in lines 3, 4, 6, and 7. And we define 4 different distinct matrices that we can use as input objects for our models later on. And last but not least, some of our models do this anyway, but we want to use our own functions, r squared and RMSE. So actually this is the r squared. As you can see, it includes as inputs the predicted and the actual values. And then you can calculate the RSS, the TSS, and the r squared is simply 1 minus RSS divided by TSS. That's what is returned in line 5. And the relative mean squared error is just the square root of the mean of the squared differences between the predicted and the actual values in line 9. So we'll start with OLS, with a simple linear regression model. So we forecast the future Apple returns with past returns of the stock itself and various other variables, and we use lin model. That's the object that we are defining. Is LM, linear model, that's the R code for a linear model. Forecast, that's the column of the Apple returns 1 day ahead, being a function of, and as you can see here, if we don't specify any variables and only put in a point, full stop, this means that all the variables that are included in training data can be used or should be used by the program as predictors. And what happens is, as you can see here, we are using a simple linear regression model that includes all predictors. And we have the intercept, we have Apple stock returns, Microsoft, Amazon, Google again, JP Morgan, Johnson & Johnson, and this is where Johnson & Johnson becomes interesting because, as you will see on the next slide, Johnson & Johnson, the stock return on the Johnson & Johnson stock is the only predictor that is statistically significant, at least at the 10% level. All the other variables are not statistically significant. It goes on with the 5 macroeconomic variables, and the multiple R squared is quite low, and the adjusted R squared is even lower. It's almost 0.1%, and as we will see later on, it doesn't get too much better using rich regression, Lasso, or the elastic net. Slightly better, but what we can already see here, none of the predictors really has too much explanatory power for explaining and forecasting future Apple returns. Remember that we haven't put in any theory into this. We are only using all available data to forecast future stock returns. This is typical of machine learning. In an economic model, we would have argued that there are some variables that should have an impact on future stock returns. We probably would have used a time series econometrics model. This is simply statistical learning. We're using all the data we have, we're using all the predictors we have, and it turns out that for some reason, the Johnson & Johnson stock return has a slight statistical significance in explaining future Apple stock returns, but as we can see from the R squared, it's not too helpful. Okay, we can then predict from this linear model. We're using test data as the new data, and the R squared and the relative mean squared errors. On the test data, well, they're given here. The R squared becomes negative, and the MSE is 2.4%. This is rather dismal. As we can see, it doesn't generalize well to the new data. So as the in-sample fit of the linear model was already not too good, it's not surprising that it doesn't perform better on new data, and actually the R squared becomes negative. Now, to use rich or Lasso regression, remember that we have one tuning parameter, both in rich and Lasso, and we have 2 tuning parameters in the elastic net, and we need to choose the tuning parameters such that it generalizes well to the new data, and this is done via cross-validation. Remember, cross-validation means that, for example, leave one out, cross-validation, you leave one observation out, and you fit the model on the remaining objects, and then continue to do this until you've run through all the data observations. In Kfold cross-validation, you split the training data into K parts, or so-called folds, and usually you choose 5 or 10 folds. And then Kfold cross-validation considers training on all but the kth part, and then validating the model performance on that kth part, iterating it over all K parts, all K folds, and then estimating the relative mean squared error, for example. And then you choose the hyperparameter that performs best. For example, in each model, you can use different types and different values for the hyperparameters, which in this case is the tuning parameter. And then you choose the parameter that reduces the MSE, that yields the lowest MSE. And this is how it's done for the rich regression here in R. First of all, we're using the glmnet library. We set seed, use the set seed command for reproducibility, so that if you do this again in R, you get the same results, because there is some variance, of course, in this process. But if you use the set seed command, you can always reproduce your initial results. We then will find the optimal lambda parameter via cross-validation. We are using 10-fold cross-validation. Each time we will use 100 regularization parameters, tuning parameters, that are tested in each of these n folds. And we'll start actually here. If we set alpha, the weighting to be used, to 0, this yields us rich regression. Later on, if we set it to 1, it will give us the Lasso. So this is the command cv.glmnet, and this cross-validation for the rich regression will use the X train matrix and the Y train matrix, the training data, to select via cross-validation the parameter. And after some time, you can see here in the lower part of the slide, we get an optimal lambda tuning parameter of 0.4556. We can then fit ridge regression, which is very simple, GLM net alpha equal to 0, so that we get ridge regression. Lambda is the tuning parameter. We use optimal lambda, selected via cross-validation here. And then as data, we use X train and Y train. And here you can see the coefficients of the ridge regression. Not surprisingly, if you remember the video on ridge regression will usually include non-zero parameters for all predictors. So it's not surprising that we have all those parameters included in our model, and Apple, Microsoft, Amazon, and so on, all these predictors are in our regression. You all will also remember that if we set the parameter lambda to 0, we get OLS. If we set it to infinity, all the parameters will be forced to become 0. And if we do this now with a high lambda and a low lambda, you will see what happens. For example, if we set it to high lambda, then we get this. And if we do it with low lambda, we'll arrive actually at the OLS coefficients. Okay, now to see how ridge regression fares in comparison to OLS, let's have a look at the in-sample R squared. If we use it with the training and training data, you can see that the R squared is 0.0003, which is much lower than in the OLS model, which was 0.007. Well, it's lower at a very low level, of course. The out-of-sample performance, we again predict using ridge regression now, and look at the R squared, it's minus 0.005 in comparison to minus 0.0138. So it's slightly better. Actually, the out-of-sample performance is slightly better when looking at the R squared, and it's also better when looking at the MSE. So this is one finding. So we use tenfold cross-validation to determine the hyperparameter lambda. Why is this, by the way, called a hyperparameter and not a parameter? Well, it's used, it's a parameter that governs the training process. If it is a parameter that is used in the training process, it's a parameter. But if it governs, if it changes the way the model learns from the data, this is called a hyperparameter. So lambda is a hyperparameter because it shifts from OLS to ridge regression, for example. And using this lambda, we obtain a linear model with coefficients that are smaller in terms of their absolute value than the OLS coefficients. And the OLS model achieved the highest in-sample R squared. However, the out-of-sample performance was better for the ridge regression, slightly and at a very low level, but nevertheless, out-of-sample performance was better for the ridge regression. We can now do the same for the Lasso. Again, we use the GLM net library. We use the setseed command to be able to reproduce the results later on. And then CV Lasso is, first of all, the cross-validation selection of the hyperparameter. We set alpha to 1, so it's not ridge, it's now Lasso. And we get the optimal Lasso in line 10. We then fit the Lasso regression model to the data, to the training data, using alpha equal to 1. So we're using Lasso, and we are using the optimal lambda. And as you can see, now several of our predictors are actually left out of the model. This was the main difference between Lasso and ridge. Lasso can exclude variables, whereas ridge regression usually will include all predictors. And here, not surprisingly actually, what is left in the model is the Apple stock return itself. So this is indicative of the fact that yesterday's stock return of Apple will probably predict today's stock return on the Apple stock. So this actually makes sense in an economic way, but it could have turned out anyway, in any other way, of course. So this is what we can see In sample R squared is 0. The out of sample performance measured by the R squared and the RMSE is again slightly better than in the linear model. For example, you can see the MSE is 0.023 in comparison to 0.024 in the OLS model. So this is the Lasso. And last but not least, we can also do the same with the elastic net. Now we use the Caret library, again, make it available for reproduction. And then we need to select the two parameters. This is done via cross-validation again. And then in the end, in lines 8, 9, and 10, you can see that we are training the elastic net using forecast, all variables, the training data, and the training control object for the parameters. You can see the optimal parameters are alpha and lambda, 0.81 and 5.48. And then again, based on the optimal parameters from the previous slide, we can predict our data on the training data. The R squared remains at 0, and the out of sample predictions and performance is again slightly better. But if you compare, for example, the RMSE for the elastic net, 2395 compared to 2395, 205, 205, it doesn't get better. It's actually the same for the Lasso and the elastic net. So this is an application of those penalized linear regression models. And next, in the next section, we'll talk about classification via k-nearest neighbors and support vector machine.